Section 5 of Chapter 9 relates the gas laws that we've been looking at to a theory of gases. This theory is a model of how to picture gases that makes it agree with the behavior of gases that we see and measure in the gas laws. So just a little reminder of the difference between a theory and a law. A law is an observed pattern or relationship. A lot of times it's a mathematical formula, like our Boyle's law and Charles' law that we have seen. And the theory is the model to explain the reason for these observations. So the laws themselves do not give an explanation why we see this behavior. They just detail the pattern of the behavior, sometimes with a mathematical formula. And then the theory is what we're using to explain the reason for these observations. And so I urge you to take a look at your textbook and read about the different types of ways that you can relate this theory to the laws that the theory is trying to explain. So here's just a summary here that gas particles are seen as small particles that are in constant motion in straight lines, and then they collide with either the container walls or with each other. So that can help explain Avogadro's law that if you have more particles, remember Avogadro's law is that V1 over N1 equals V2 over N2, or the fact that the volume is proportional to the amount of gas, the number of moles. So the more moles that you have, the larger volume it's going to take up if you are keeping the same pressure and temperature. So they need more space to be able to have similar collisions if there are more particles. The compressibility of a gas is explained by the theory that the particles of gas are very small compared to how much distance is between them. So they're going around really quickly in a container, and there are large distances in between the particles, and so if you squeeze them, you can compress these distances, these empty spaces that are between the particles. Then the collision of particles with the container walls creates pressure, and this can help to explain or visualize what's happening with Boyle's law or Charles' law. If you decrease the volume, you're going to have more collisions with the container wall, so that's going to increase the pressure. Or if you increase the temperature, then to keep the same pressure, you're going to have to increase the volume. This also comes into play in the Guy-Lussac law, because if you increase the temperature, it's going to increase the collisions and increase the pressure. If the volume doesn't increase, it's going to increase the pressure. So either the pressure or the volume has to increase from these more forceful collisions. And the higher temperature gives these particles more kinetic energy, and so it does make these more forceful collisions to the walls of the container, increasing the pressure or increasing the volume. So both Charles's law and Guy-Lussac law are explained by feature of the theory listed 3 or number 5. So there's a little bit of, there's overlap. It's not like this explains this law and this explains this law. It's just that these are features of the model that we are presenting, and they agree with a lot of the laws that we've already seen. And then the observation that we are treating these gases just as a nameless general gas. We don't say, oh, oxygen gas does this, and chlorine gas does this, and nitrogen gas does this. We're just treating all these gases the same. And that observation is explained by a theory that these gas particles are independent of each other. They don't attract other gas particles or repel other gas particles, and so it doesn't really matter which type of gas you have, what the identity of the gas is. So this explains Dalton's partial pressure. So it doesn't matter which gases are mixed together, their pressures just add no matter what. It also helps to explain the ideal gas law, where all of these gases behave in the same mathematical way, independent of their identity. These are just some ways that the kinetic molecular theory of gases agrees with and helps to explain the laws that we've already talked about. All right, so let's go a little bit more into looking at temperature and how it relates to the kinetic energy of the particles. Let's take a look at this Maxwell-Boltzmann distribution of the speeds of different molecules of gas or different gas particles. Sometimes the gas is an atom. What we have here on the y-axis is the number of molecules, the number of gas particles that have a particular speed, and then on the x-axis is the speed of the particular particle. So the temperature is a measurement of the average kinetic energy because we have a lot of different gas particles, and some of them are moving slower and some of them are moving faster. We have a distribution of speeds. So this peak at the top is the speed that the most molecules have. So this is the most likely speed that a molecule could have because the most molecules have that particular speed. However, it's not even on both sides of the curve. We have a little bit of a tail in the positive direction because we can have more molecules that have slightly higher speeds. We can't really have any molecules that have a speed below zero. That's kind of the hard limit there. So we have a little bit more on the upper speed range, and so the average speed is actually a little bit above what this peak speed would be, what the most molecules have. The average speed is a speed a little bit faster than that, and this is called the root mean square average speed of this collection of gas particles. And so this one is a representative of oxygen gas at 300 Kelvin because this distribution looks different for different gases because it is dependent on the mass of the gas molecule, and it's also dependent on the temperature. So let's take a look at what changes you can see with different gases and with different temperatures. So here we have a similar graph. This is using the gas nitrogen. Again, we're going to compare the same gas at different temperatures because both the mass of the gas and the temperature affect this distribution. So we want to change just one thing at a time. So here we have the same gas but at different temperatures. So as you increase the temperature, then the average speed is going to get higher and higher, and the curve you can see kind of gets flatter and more spread out. So even at this very high temperature of 1000 Kelvin, we still have a few molecules that have quite a low speed, but then we have more molecules that have a very high speed. So we have some molecules here that at 1000 Kelvin you have some that have a speed of 1500 meters per second, whereas at this lower temperature of 200 Kelvin there's really no molecule that has a speed that's that high. So the curve, as the average moves up, the curve kind of gets flatter because the spread of the possible speeds of the molecules is a larger range at higher temperatures than it is at a lower temperature. Okay, and here we have another interesting graph. It compares molecules of gas that are at the same temperature, although it doesn't say what temperature it is, it just says a given temperature. But these molecules are all the same temperature. We have from the lightest to some heavier molecules, and the lighter gas at that same temperature has to have a faster collection of speeds in order to have that same average kinetic energy, because remember that's proportional to the mass as well. So in order to have a certain kinetic energy, a certain average kinetic energy, which all of these would have the same average kinetic energy if they're at the same temperature, in order to have that same energy, the lighter molecules have to be moving faster, and then as you get heavier and heavier, you can have a much slower speed. So it's very similar to the nitrogen that we saw in the previous chart. When it was at a low temperature, it had a sharper curve at the low end of the speed spectrum here, and when it was hotter, it had a more spread out curve with a higher average. For lighter gases, the curve shifts to the right, and as it shifts to the right, it gets flatter, just like it did for the higher temperature. The same kind of shift is seen for lighter molecules. So that's kind of interesting. We have seen the kinetic energy of a particle before when we were talking about the photoelectric effect and an electron being ejected with a certain kinetic energy. We use this formula that the mass of an electron times its speed squared divided by 2 would be the kinetic energy of that individual electron. When we are talking about gases, each of the molecules has a different kinetic energy because we have that spread, that Boltzmann distribution of different speeds that the particles are traveling. And so when we talk about a mole of gas, it's not very convenient to talk about the kinetic energy of each gas particle in a mole. Of course, a mole is a crazy big amount of particles. And so it's more convenient to talk about the average kinetic energy of the mole of gas. So instead of the mass of the individual gas particle, you have the molar mass, how many grams per mole you have. Actually, if we're going to relate this to meters per second and have SI units, we're going to be talking about the molar mass in kilograms per mole rather than grams per mole. So we have that here. We have to have the molar mass in kilograms per mole. So this becomes sort of a issue of having the correct units in our calculations. And then instead of having the speed of the individual particle, we have the root mean squared speed of the distribution of the mole of particles. The average kinetic energy of a mole of gas is also proportional to the Kelvin temperature. And that means it's proportional, so it's equal to a constant times that Kelvin temperature. And that comes out to be 3/2 R. So 3/2 R times the Kelvin temperature is another thing that's equal to the average kinetic energy. So if we set these two things equal to each other, since they're both equal to the average kinetic energy, if we set 3/2 RT equal to 1/2 molar mass times root mean square velocity, and we solve for the root mean square velocity, we come out with this equation over here. That the root mean square velocity is 3RT over the molar mass, and then the square root of that entire amount. So then the only challenge remaining is to put R in the correct units and to get the molar mass in kilograms per mole, which is a bit unusual. That's not what we usually see. But once we do that, we can have the units cancel and get a speed in meters per second. The root mean squared velocity then is 3RT over m, the molar mass. So we're going to figure out the root mean square velocity of a sample of argon gas that is 34.5 degrees Celsius. So this 34.5 degrees Celsius has to be converted into Kelvin. So we've been doing that all along for these gas laws. And also argon is 39.95 grams per mole. Just an atom of argon is argon gas. And we need to convert that into kilograms per mole. So we need to divide that by 1,000, and so we come out with 0.03995 kilograms per mole. So here we have kilograms per mole. The mole is in the numerator because we're dividing by kilograms per mole. So we have kilograms in the denominator, moles in the numerator. And then for R, instead of using our liters, atmospheres per mole Kelvin, we are using this value. So 8.314. Another unit for R is joules per mole Kelvin, and joules are kilograms meters squared per second squared. So we have reduced this to just the SI units. We've replaced the joules even with kilograms meters squared per second squared. And then we have per mole Kelvin. So this is the one that is most useful in this equation because we have the 8.314 kilograms meters squared per mole per Kelvin per second squared. So these are all the units for R. This is the temperature. We have 3, so we have 3 R, T, and then we have the molar mass in kilograms per mole. And since we have that, the kilograms are going to cancel, and the kelvins and moles are going to cancel. So we have moles and kelvins. And we're going to end up with meters squared over seconds squared. So this ends up being 192,106 meters squared per second squared. We only have 4 significant digits, so I'll underline that. And then we have to take the square root of this. And so the meters squared per second squared is going to become meters per second, which is reasonable for speed. And then this is going to become just 438.3. So then the root mean squared velocity is 438.3 meters per second.